Welcome to a visual summary of my experiment, which aimed to design and construct the lightest possible spaghetti bridge with the highest self-weight to applied load ratio. For this point load experiment, I've designed a cable-stayed spaghetti bridge with 3 Warren trusses forming the deck. I have chosen a proven Warren truss system with double vertical members to distribute the point load evenly across the 350mm single span. Cable stay towers just inside the point of the rollers use a harp system of tension cables to pull the central point load back to the supported ends of the bridge. This presentation will analyze the predicted and actual failure load scenario as demonstrated in the video available on the Part B ePortfolio page. Initial sketches were drawn based on researching various truss configurations and bridge structures. I then chose to design a cable-stayed system to utilize the tensile strength of spaghetti. As you can see from the space gas images, the conceptual design is a combination of a Warren truss deck with its main span supported by cables. 5.5mm diameter solid steel tubing was used to represent spaghetti in this model. The spaghetti bridge was constructed using dry spaghetti connected with Celsius Quick superglue. Firstly, strands of the spaghetti were glued together in a stretcher bond configuration to form a 500mm top cord for the trusses. This process was repeated to create the 3 top cords and 3 bottom cords. Once dry, vertical and web members were added, creating 3 completed Warren trusses. Secondly, 3 spaghetti strands were laminated together with glue to form 2 towers. The base of each tower was glued to the central truss. Thirdly, the 3 trusses were glued together with the towers attached to the central truss. This formed a triple layer truss beam 500mm long. With the 3 panels now connected, 5 cable members were attached between the lower central gusset and 3 points of each tower. On the outer side of the towers, 9 cables were attached down to the lower cord at 2 points. A flat loading platform was created at the center of the bridge using lateral diaphragms and struts. Finally, roller plates were attached to the base of the bridge structure at each point of support. This, along with extra spaghetti on the top cords, was used to stabilize the structure laterally. As part of the design process, I built a 1:1 scale model in the space gas analysis program. The static load analysis tool was used to test a point load of 9.8 newtons, or 1 kilogram, which is over 10 times the self-weight of the 90-gram bridge. The results of which demonstrated minimal deflection of the structure. From these results, it was estimated the bridge would support a point load of at least 10 times its self-weight. Based on further testing, a failure weight of 1.5 kilos or 14.7 newtons is predicted as the axial force demonstrated becomes extreme. The tear weight of the loading plate, hook and bucket was 230 grams. The self-weight of the bridge was 90 grams. A metal loading plate was placed on the loading point of the structure, attached with a hook to the load bucket. Loading commenced with scoops of ballast added to the bucket, with intermittent pausing to assess deflection. Several scoops were added until 1 scoop before failure, a lateral deflection was noticed in the trusses. The final scoop was added. During a pause, the bridge tipped suddenly, resulting in the 2 towers laying horizontally. Once the testing was complete, the gross weight of the bucket, ballast, and loading plate were weighed, which showed the point of failure to be 1.94 kilos, or 19 newtons. It is concluded that the structure of 90 grams supported up to 21.55 times its self-weight before failure. This failure weight exceeds the predicted failure force of 15 newtons. The weighing process can be seen in these images. The bridge exceeded the predicted failure load within the constraints of the assignment. This design has effectively used the tensile strength of spaghetti in a cable-stayed harp system to redistribute a central load back to the support rollers. The Warren trusses also spread the point load back to the rollers. Failure was due to lateral deflection of the structure, causing a displacement in the applied load, which caused the structure to tip. Feedback from the peer review supports the findings that the lateral load displacement caused the bridge to tip and fail. Static analysis in space gas did not account for the load movements or sway, and did not predict this failure scenario. An improvement to this experiment would be a consistent centered load flow from a funnel rather than heat ballast causing live loads, such as bounce and sway. This tandem system would be an effective solution if the towers could be attached to piers or foundations as used in the real world. This experiment has shown that space gas underestimated the failure load for this structure, with an applied load of over 21 times its self-weight. Lateral deflection was not accounted for and caused for the failure of this structure in this experiment. It was interesting to see the failure conditions of piers bridges during the design phase. These were taken into account during the construction phase of this bridge. Load movement through the structure was clearly visible as the bridge began to deflect laterally. This emphasizes the necessity to keep static loads static. Overall, the experiment highlighted the effectiveness of cable-stayed tensile members and the strengths of the Warren truss configuration in redistributing point loads.